Hi, this is Chanel, Alex, and Aditi from Team B2, and this is our capstone project, Robotic Indoor Plotting. The problem we set out to solve is that Google Maps lacks accurate and comprehensive indoor positioning information. Indoor positioning information is valuable for better navigation of indoor spaces and a lot of applications for consumers, facility administrators, and eventually autonomous systems like delivery and navigation bots. What we built is a robot that can autonomously map out the floor plan of an indoor space. The user gets back a 2D floor plan and can do whatever they want on top of it. We built this using a Raspberry Pi 4 on top of a iRobot Create 2 base with a RP LiDAR doing 360 scans on top. To use it, you just set it down facing the direction you want to be north on the map and tell it to start mapping. It'll navigate until it's done, which is when it's fully enclosed by walls and has explored everything within the walls. When it's finished, it'll automatically stop and send the final map as an image to a web app where the user can do whatever they want with it. This is ultimately a multi-threaded program running in real time, with SLAM reading in from the LiDAR sensors to construct the map, navigation and control systems to choose destinations and paths. It has obstacle detection for interrupting if there are obstacles and walls, and finally, a robot move execution thread. This is the flow of data that travels throughout our program. So first, it starts with a raw LiDAR scan. These are raw scans that are coming from the RP LiDAR, and although they don't look like much here, they're also represented in two separate arrays containing points. The points are represented as distance and angles and help construct the map that we use later. Those two arrays are fed into BreezySlam. BreezySlam is a Python package that integrates well with the hardware we have. It has limited tuning, but it's really easy to use and works pretty well. It stitches scans together as the robot moves, and it also keeps track of position. If you can see on the diagram, the little dots are where the robot is traveling and the path that it takes when it moves throughout the map. This is then fed into our custom program map data. This is something that we created to represent the map as the robot explores. After doing some compression, this map is labeled with red representing the robot's current position, green representing the robot's destination it's trying to travel to, yellow is the path that it's going to take, blue are walls that it identifies, and then orange is padding that we labeled around the walls so that the robot doesn't bump into them. Finally, after updating this map data as it explores, the robot generates a final user map. We bring the resolution back up a little bit so it's a little bit more pleasing and we get better features for the user. And this is the final map without all the internal information that we had before. That's displayed to the user.
Now let's look at the robot in action. Our first test case is our team member's bathroom. From the picture, you can see that it's a relatively small room with obstacles lining the walls. Here's the terminal output from running the program. First, the robot performs some initialization. Then it takes the initial scan and immediately realizes that it's inside a closed polygon of size 11 pixels. This is smaller than our pre-calculated threshold of 4,800 pixels. Therefore, we conclude that we have fully scanned the entire room and we terminate the program. Shown here is the internal data map. This is the compressed map that we use for internal data storage, as well as for navigation processing. In the middle of the map, you can see the red pixel indicating the robot's location. The blue pixels represent the walls, the orange pixels represent obstacle padding, and the white and gray pixels represent explored and unexplored areas, respectively. In the bottom right of the map, there's a 1 meter long black line for scale. Shown here is the raw output of the SLAM package. This image is very high resolution. In fact, it's 800 by 800 pixels, which is infeasible for any sort of navigation processing, hence our high compression for the internal data map. Finally, this is the map as we would show it to the end user. With some autonomous cleanup, we've removed a lot of the blurry lines, keeping the resolution relatively high, and also solidified some of the existing walls in order to make it a little bit cleaner for the end product. Now let's look at a slightly more complicated test case, our roommate's bedroom. This room is quite a bit larger than the bathroom and has a lot more obstacles scattered around, which should allow for a more comprehensive test of every single one of our subsystems. On the left, you'll see the terminal output, and on the right, the robot as it's moving. As soon as the program starts, the initial scan tells us that we are not enclosed inside the room's walls yet, so the robot chooses a destination and begins to move. While the robot is moving, we are constantly taking in and stitching the LiDAR scan data with the SLAM module. However, we are not doing any navigation processing. This is to save processing cycles, since it is unnecessary to reprocess the map unless we detect an obstacle. Here we've detected the obstacle, and so we move the robot back slightly to avoid collision and then reprocess the map. Normally, we would also choose another destination and begin executing the new movement path. However, in this case, when we reprocess the map, we realize that we've gathered enough data to enclose ourselves within the room's walls, as indicated by the flood fill value being lower than our threshold. The program will terminate because of this. Shown here is the same test case, but on the right side, we'll show the progression of the internal data map. This is very similar to the data map from the first test case. However, since we've actually chosen a destination, that is represented as the green pixel currently outside the walls. The yellow pixels represent the path that we've chosen to get there. Note that as the robot is moving, the red pixel indicating the robot's position is updating. However, the rest of the map is not. This is again because we do not do any navigation processing unless we encounter an obstacle or we've reached the end of our path. Here, once we see the obstacle, the map will update all at once. We now realize that we are inside a closed polygon, so the program will terminate. Note that there's some error has accumulated on the bottom left outside of the walls. And also, when we encountered the obstacle, we added it to our map in the form of an orange pixel surrounded by the burnt orange obstacle pixels in order to avoid bumping into the same obstacle twice. Here again is the same test case, but now we'll show the progression of the map stitched together by the SLAM module. Unlike the internal data map, this map is constantly being updated even while we're moving, so this can give a more accurate representation of what our robot is actually seeing. There are some interesting things to note on this map. Again, we can see the error accumulated in the bottom left outside the walls. We think this is likely due to the fact that when we turn, we lose some accuracy in odometry, partly because of the carpeted floor and partly because the Roomba's odometry is pretty bad to begin with. Also, the table legs are represented by the 3 spikes coming out of the bottom and bottom right edges of the room. This is because we never took any scans from the other side of the table, since we already determined that we finished mapping the room. Finally, this is the map as we would show it to the end user. Again, through autonomous cleanup, we removed a lot of the junk pixels and blurry lines. However, we were not able to completely eliminate the error in the bottom left. In spite of this, the map is still good enough for a human to get a general layout of the room. Throughout the course of our project, we overcame many challenges, but many still left an impact. The COVID outbreak caused a number of logistical issues. We lost access to hardware such as the fabrication labs, soldering, and other peripherals normally available on campus. Since all of our hardware was in one place, our testing had to be done remotely through Zoom, and the testing that we could do was limited to our teammates' bathroom and bedroom. We needed larger and more structured areas for good tests. Our decision to use the Roomba as a mechanical base caused some headaches as well. Some sensors would get stuck, and there was no way to fix them besides restarting the robot. Other sensors were just flat out wrong, likely due to hardware encoder bugs. There was also a persistent firmware bug that caused the robot to randomly become unresponsive, fixable again only by a factory reset. Lastly, our choice of a basic Python SLAM language meant that we had limited tuning options. The algorithm was not very sophisticated, and the stitching was inaccurate. On top of that, when we compressed the map for internal data processing, we lost even more accuracy. We learned a lot from this project, so we hope to pass on some of our key lessons.